So, for a relation, we define a inverse relation. For any relation R from a set A to B, we define a relation R inverse from B to A. But for a function, suppose f is a function from A to B, then f is also a relation from A to B. As a relation, we can take the inverse of that, and that will be a relation from B to A. But that relation need not be a function. Inverse, suppose f is a function from A to B, there is a relation from A to B. As a relation, that is having an inverse relation. But that inverse relation need not be a function. For example, you take something like this: 1, 2, 3, A, B, C. You put 1 to A, 2 to A, and 3 to B. This is a function. Suppose that I call that function. What about the inverse function? A, B, C. 1, 2, 3. F inverse is of course a relation, but how is that relation behaving? A is related to 1, A is also related to 2, B is related to 3. This is the inverse relation. But this inverse relation is not a function for two reasons. One reason is that this element, this is related to no element. So one condition of the function is violated. And another condition is that the same element A is mapped to 1 as well as to 2. So this relation is not a function. So the inverse of even when a relation is a function, its inverse relation exists, of course, the inverse relation exists, but that may not be. So the question is, when does this exist? When the inverse of a function exists. The inverse of a function exists in a special case where the function is a bisection. So let the f be a bisection. Sometimes people call a bisection 1, 1, 1, 1, 1, 2, or sometimes people say 1, 1 corresponds. So suppose that f is a bisection, then we can define an inverse. It's a bisection means there is injection as well as a surjection. Now, you take any element of say y of b. Suppose b is an arbitrary element of b. Since f is surjective, there exists an x element of A such that f of x is equal to y, or such that xy is an element of f. So such an x exists because of the surjectivity. Because the function is injective also, this x is unique. Because there is no other, say x dash, such that x dash is also related to. If that happens, then x is equal to x. So this x is unique. So there exists a unique x in A such that f of x is equal to y. So for every y in B, there is a unique x in A which is mapped to. Then we can define a function g from, we can define a function f inverse from B to A by f inverse of each element y is defined as x if f of x is equal to, when f takes x to y, f inverse takes y to x. Or it's just the inverse relation. When f is a bijection, this inverse relation also becomes a function. And only then this happens. Because if f is not subjective, what happens? If f is not subjective, there is an element of B to which no element of A is mapped. So this element cannot be mapped to any element. Another, suppose the function is not injective, then what happens? There will be two different elements of A mapped to the same element. So the inverse will take one element to both the elements, which is not possible for a function. So the inverse relation is a function if and only if our original function is bijective. So for bijective functions, the inverse can, and only for bijective functions, inverse can. So this function f inverse from B to A, defined as here is called the inverse function. Inverse function or inverse of the function. Clearly we have the formula f composition f inverse is equal to f inverse composition f is equal to, sorry, f inverse composition, this will be identity, this will be from, this will be identity on B, and the f inverse composition f will be identity on A. Because if you take any element of B, first apply f inverse, then apply f. Then it will be mapped to the same element. So that will be this. Or you could take an element of A, apply B, apply f, then you apply to that element f inverse, you will go back. So f combination f inverse is the identity on B, whereas f inverse combination f is the identity on B. In fact, we can prove that these two properties, these two equations define the inverse. That is a function f is bijective if and only if a function f from A to B is bijection, is a bijection. If and only if there is a function g from B to C, such that g combination f is a function is equal to the identity function A, and the function g is a function I is equal to the identity function. And in this case, we will get that g is the inverse of. So this happens is similarly. So we can also define the inverse of a function like this. There is a function g from B to A is called the inverse of a function from A to B if and only if g composition f is identity on A and f composition is identity. Now, how to prove this theorem? First, we assume that f is a bijection. Then you want to prove that there is a g from it. Very easy. You just take g to be equal to f inverse. Then that is all. Conversely, suppose there is a g satisfying these two conditions. Then we can prove that f is bijective. How is that done? First, we want to prove that f is say injection. So f is from A to B. So take x, y elements of A. We want to put we want to take we take f of x is equal to f of y. Then we have that g of f of x is equal to g of f of y. But decomposition of this identity, therefore we get that x is equal to. So f is the disjunction. Now we want to prove that f is a surjection. How to prove this? You take an element, say y of p. Now, g is a function from B to. So, we can take g of y, and g of y will be an element of A. Now, what is f of g of y? That will be an element of B. Because g is a function from, sorry, f is a function from A to B. But what is g of this? This is nothing but g compression f of y. And what is g compression of it? So that's equal. So that we will get that g compression. So g of f takes g of y to x. So f takes g of y to y. That means y occurs as the image of some element of. So surjective also. So once we have this condition satisfied, then f is 1, 1, and 1. And that g is nothing but the inverse of r. So this property is actually a characterizing property of the. Suppose f is a function from A to B and g is a function from B to C, and suppose that both are bijections. Then we have that f conversion, so g conversion f from A to C is also a bijection. Why? Composition of bijective maps is again bijective. Now, if decomposition f is bijective, then inverse of decomposition f. And what is decomposition f? It is nothing but f inverse composition g inverse. So what is the proof? We need not prove it. Why? We proved it for relations earlier. And functions are special cases of relations. So we need not give a different proof. Of course, we can give proof in this context easily, but of course this follows as the special case. But the problem is that this question arises only when this property holds only when f and g are bijections. Because otherwise f inverse g inverse will not exist. And f conversion, g conversion f inverse also. So the inverse of g conversion f is nothing but f inverse conversion g inverse. Now that's here, when you take the inverse, the order is reversed. And there is a question. Suppose you are having H composition, G composition. There is a f is a function from A to B, G is a function from B to C, and H is a function from C to D. In that case, actually we will be having H composition, G composition F, and as well as H composition, G composition F. But both are one and the same by the associativity. So we need not put brackets. So there is no point in putting in brackets. So we can write just like H composition, G composition. Now what is the inverse of that? If F, G and H are odd bijections, this is also a bijection, and the inverse is given by what? F inverse composition, G inverse composition, H inverse. you can deduce this from the previous one. And of course, you can do it for any finite number of functions. Note that here, when we take the inverse, the order is reversed. This principle is used in one textbook. This principle is called the dressing and undressing principle. Because when you undress, you do it in the reverse order. The last thing we put on, we take this. So this principle is called the dressing and undressing principle. In the last class, I think I had defined the image of a set. Suppose f is a function from a set A x to y. F is a function from x to y. And suppose A is a subset. Then we define f of A as the set of all f of x, where x is an element. There is A is a subset of x, and we take the images of each elements of A and take it as a set. And that set is denoted by f of A, and this is called the image of A under the function or the f image of. And what will be this? This is clearly a subset of y. So corresponding to each subset A of x, we will be getting a subset of y called the image of x. Formerly, first we had the image of an element. If we are having an element say x of x and y of y, such that xy belongs to f or y is equal to f of x, then this y is called the image of elements. This is a generalization of that. Here we are defining the image of a set, subset of. It is defined as the set of all elements to which the elements of A are mapped. So one question: what will be f of y? Clearly that will be equal to 5 because y contains no element. So the set of all x is that the set of all f of x is that x is element of phi is nothing but phi. So the image of phi is phi, and the image of x is the range of, it's called the range of. So, if A and B, if A is a subset of x and B is a subset of x, and x is a function from x to y, then we have f of A union B is equal to f of A union f. For the image of a union is the union of the images. How to prove this? Say y is an element of f of A union B if and only if when y is an element of the image of A union B, if and only if there exists an x element of A union B such that f of x is equal to y. Now, when does this happen? X is an element of A union B means x is either element of A or element of B. So there exists x element of A or x element of B such that f of x is equal to that is either there exists an x such that there exists an x element of A such that f of x is equal to y, or there exists an x element of A such that f of element of B such that f of x is equal to y. And this happens. The first thing will happen if and only if y is an element of f of A, and the second thing will happen if y is an element of f of B, and this is logically equal to y element of f of A union f of. So what we proved is that f of A union B is equal to f of A union. So image of a union is the union of the. If you get such a result about unions of two sets, it is natural to ask does there exist a result for intersections? So the question is whether f of A intersection B is equal to f of A intersection f of B. No. Okay, let me take an example. A, B, C, etc. T is 1, 2, 3. Here. Suppose A goes to 2, B goes to 2. When C goes to 3. Here f of singleton A is the set containing 2. F of singleton B is the set containing 2. And what is the set F singleton A intersection of singleton B? That is f of the empty, and that is equal to empty. So here f of A intersection B is not the same as f of A intersection. Note that here we are violating the injective condition. The function is not an injection. So it's not, this result is not true. But of course you can see that if f is a function from x to y, then suppose a is a subset of b is a subset of x, then we can see that f of a is a subset of very straightforward. Because every element of A belongs to this set contains only images of elements of A, but every element of A is also an element of B. So all of them will be the image of. So A subset of B implies that f of B implies that f of A subset of B. So A intersection B is clearly a subset of A. Therefore, f of A intersection B is a subset of f of A. A intersection B is also a subset of B. Therefore, f of A intersection B is a subset of B also. And since this is a subset of f of A intersection B is a subset of f of A, B. Consequently, we get that f of A intersection B will be a subset of f of A intersection from this and this. So f of A intersection B is a subset of f of A intersection F. This part will, the other part will not, because in order to show this result, we have to prove two things. F of A intersection B is a subset of this, and this is a subset of f of A. So one part is true, the other is not in general. But for a union, there is no problem. The image of a union is the union of the images. The image of an intersection need not be intersection of images. But if f is an injection, this is if f from x to y is an injection, we have that f of A union A intersection B is the same as f of A. I am not proving this. Proof is left with yourself. So for injective function, this is the result. In the last case, we failed to get this. We obtained a counterexample because our function was not injective. I am also suggesting another exercise. We observed that f is a bijection from A to B. It's a bijection if and only if there exists a G from B to A such that G convolution S is equal to identity on A and F convolution P is equal to A. In algebraic terms, if this condition is satisfied, if these two conditions are satisfied, means in the algebraic terms we say that G is the inverse of F. And if you consider only one equation only, this means G is the left inverse of F. And this means G is the right inverse. And inverse means two-sided inverse. So left and right inverse. So a two-sided inverse exists if and only if, or f is invertible if and only if it is a projection. That is the result. We can ask a related question. When do we get that a function is having a left inverse, or when it will have a right inverse? For a function f from a to b, there is a function g from b to a such that g composition is equal to the identity on a and do it. Another question is for a function f from a to b, there exists a function g from b to a, sorry, g from is such that f composition g is equal to g identity on if and only what is the condition? Let's say function is having a two-sided inverse if and only if it is a projection. It will be having a left inverse if and only if what condition is satisfied? Similar question for right inverse. That is to take an element of b, say y is an element of b, then ip of y should be equal to f composition g of that. That is f composition g of on y means f of g of y. So f of g of y is equal to that. That happens if and only if the function is onto. So this happens if and only if f is a subset. And this happens if and only if f is an. Say function has a left inverse if and only if it is an injection. It has a right inverse if and only if it is a subjection. And it is having an inverse if and only if it is both an injection and a subjection, that is, it's a projection.